This is the 36th lecture in a series on heuristic search, single agent search. And in this lecture, we're going to be looking at a general topic, but with particular applicability to the differential heuristics that we were looking at in the last lecture. And the topic is going to be selection of heuristics. So this is in particular subset selection of heuristics. And the idea here is that we have many heuristics that we can choose from, and we want to choose some subset of them. So if you remember back, we did discuss a little bit in good and bad inconsistency. We said that we may have many heuristics to choose between, and we can choose between them randomly. And that would, if we are able to compensate for the inconsistency that results, then we can get fairly good performance that is close to actually having the maximum of all heuristics. What's going to happen here is that basically we could imagine that I could build all pair shortest path data. And of course, if I didn't know I had all of it, I might take sort of the max of every possible heuristic I could get. And that's going to be a very expensive process, both to look up every heuristic and to, given that I have the heuristics, to actually just store them in memory. And so we may not want to do that, but we may want to ahead of time say that we're going to select a subset of heuristics that we think are going to be generally applicable. And the idea here is that, so we want to choose some heuristics, and then we want to get those that maximize the value. And so I'm going to write this out fairly formally today, just to make sure that we're clear on exactly what's going on here. And to be, just to say, this is a general technique. It can be used for any type of heuristic selection process. And so that's very valuable, and it's important to think about using this in a broad range of problems. So the idea here is that I want to choose a set of heuristics. So this is going to be a set here, and it's going to be a subset of all possible heuristics, which I'll call C. Or let's just say that there's C possible ones that I could choose between. And these are going to be H1 to H, whatever the size of C is. Okay. And we're going to say that I'm going to choose a set of H is the size of H is going to be D, which is the number of heuristics I want. So my task is to select D heuristics from a larger set that maximize the heuristic. And I'll define what this means a little bit more. We also can write this down in terms of having a default heuristic, like using Euclidean distance or something like that. And so what we're trying to say here is I'm going to build a heuristic. So my new heuristic, what I'm going to create here is we're creating heuristic H, which uses H, this coming from the set H. And it's going to be able to give me a query of a heuristic between states I and j. And it's going to be equal to the max of each H of x. So that's going to be a heuristic out of this set, which is an element of either H, or we also could say that we have a default heuristic. This is a union, not a U. So the default heuristic is we just put it here because we have these. It's not too hard to deal with this in practice. And then we're going to say it's the maximum of H of x over I, j. So essentially what this is the heuristic is for every heuristic that I select out of my subset or my set here, I'm choosing a subset to be my heuristic, then my H of this subset that I have is I'm going to take every element in the subset plus my default heuristic. I'm going to take the maximum of the heuristic of I and j for each of those, and that's going to be giving me my final heuristic here. Okay, so I have a whole bunch that I'm going to take the max of, and it's going to tell me what my performance is. And the idea here is I'm going to write this as in terms of an optimization formulation. So we haven't been doing too much of this in the class, but this is fairly straightforward from what we're used to. If you're from a machine learning background, then of course this will be familiar as well. And so we're going to write down a loss function. So, So we're going to write down a loss function here. And the loss function basically tells me what is the error that is existing between the actual state space, between actual distances. I'm going to write my L just a little bit smaller, and the heuristic that I get back out. So what I'm going to think about, my loss over this heuristic set is going to be equal to the sum from I is equal to 1 to n, and it's going to be the sum from I is equal to 1 to n, if there's n states in my state space. What we're going to do is we're going to put a weighting function here. So we're going to be able to weight certain states. And this would be, for instance, suppose that there's a fixed goal state. So I don't care about the weights between arbitrary I and j. There's only one j that I care about. Then this weighting function here would allow me to say, hey, if it's between two states where one of them isn't the fixed goal, then we wouldn't have to include this in the weight here. Practically speaking, of course, you can get rid of the second summation. But anyway, this allows us to do this in a general way. And then what I want to measure is the distance, the difference or the error that exists in the heuristic. And so what I'm going to write here is where C is going to be the true cost to go from I to j. And then I'm going to subtract my heuristic, which is going to be this h of I of j. And so essentially what I'm doing, if we set the weight to be 1 everywhere, then I'm just really adding up for every pair of states what would happen if I computed the true distance and I subtracted actually the heuristic distance here. And what we see here is that these really don't depend on anything. And this is then a negative value here. And so this is a loss. So we want to minimize this loss. But we can formulate this as the same thing as maximizing a different, which is, we'll just call this U, sort of our utility here of the set of heuristics. And this is just going to be the sum, and that's ugly. Try this again. We're just going to write here, it's the sum over I and j of W of ij times h of ij. Okay. So essentially, because, as I said, because this value doesn't really depend on the, well, it depends on the I and j, but when you add it all up and multiply it, if you were to be splitting these out, you just see this as constant. If we assume that heuristics are admissible, then we don't have to worry about the absolute value here. We could just subtract this. And so practically speaking, we want to, if all of these are admissible heuristics, then we know that all of these are going to be positive. And so then we can factor this piece out, or we can factor it out. Anyway, we can factor it out of what we're trying to minimize. And this is just a negative value. So we're just trying to maximize the actual heuristics that I want here. I need to keep the weight here. Basically what it is for any subset that we choose, this will always be exactly the same. So this is why it gets factored out. And so this leaves us with this maximization problem, and it ends up that we have two properties on U. And notice here, this doesn't say anything about the type of heuristic. I've just assumed, for simplicity, I'm going to assume that the heuristic is consistent, or sorry, is admissible. It doesn't have to be even consistent. And so now what I can notice here, and I'll explain what these are, U of H is both monotonic and submodular. Okay, so we'll explain what those are, but this is just thinking about what we're trying to do. Practically speaking, we just want to maximize the heuristics that we get over the entire state space. And so let's define these two things. And the easiest way to define these is to look at pictures here. So monotonicity. Monotonicity basically says that as I add things, so H is a set, as I add things to my set, that the heuristic value goes up. So, or this, the value here. So, so it's a function. And as we're thinking about the U function here, but I'm going to write my function as f, just because it's a general function. So monotonicity in general is a function that is going to map from, we write 2 to the s, this is the power set. This is like all combinations of elements that are within s. So if you think about like 2 to the s is the number, if you think about these as bits, where there's 2 to the s bits, and every bit says whether or not one item is in or not in the set. So it's going to map one of those sets to a real value. And what we're going to have now is we're going to have some set A, which is a subset of B, and this is going to be a subset of the entire state space. And what monotonicity says is that if you have this property, it says that f of A, so just some function, in this case my function is actually the heuristic computation, u, must be less than or equal to f of B. And just drawing this out, see if it'll, there we go. Okay, the idea here is, oh, now it's going to not let me draw my next one inside here. Okay, so we'll put this inside here. And then I'm going to need one more of these, which I'll put right there. Okay, the idea here is that we have A, or even better is, so we're just going to make this be, so we have a red set inside there. We are going to have another set inside here, which I'm going to make green. We'll make it blue. And then we have the entire state space, which will make yellow. Okay, and so what we have here, just to label these, is that this is S. Oops, I can't even write on top of here now. S, we have A, and we have B. And so the idea is that A is a proper subset of B, could be equal to, but it doesn't contain anything that's not inside B, which is, again, a subset of the entire state space, or may include the whole thing. But the idea here is that as I take A, and as I take A and I add things to it to get to B, that my function that I get here is always going to be less than what I get from B. So what's going to happen is I can never add something to a set of A. I could never add something more to it and get a smaller value back. And this is true for our heuristics, right? As I add more and more heuristics, the heuristics of the existing states stay the same, and the heuristics of the states that I haven't added to the set are only going to get better. Like I can never, because I'm taking the max basically right here in this heuristic computation, I basically can never get lower values as I add something more to it. So it just says as I go from A to B, then I'm going to keep growing. Okay, so hopefully that's fairly straightforward. And then let's look at submodularity. Submodularity is similar to this. Again, we have a function that's going to be mapping from the power set to a real number. And again, we're going to have A, which is a subset of B, which is a subset of the entire state space. But now what we're going to do is we're going to imagine that we have some X, and X is going to be an element of the entire state space, but X is not going to be an element of B. Okay, and so let me take the figure that we've done before, and we're going to copy that, make a duplicate of it, which we'll put here. And when we do this, what is going to happen? So the idea here is I've taken some X, and I'm going to add X right here. And X actually gets added. So now I'm going to use it a slightly way, but X is going to get added to, it's getting added to both A and B. And what we want to ask is what happens here. So what we're going to say is, look, if I take my function of A, where I add X to it, and I subtract my function of just A, then this has to be greater than or equal to, I'm going to run out of space on the side here. Nice thing, if I run with a whiteboard, I have to rewrite this, but I'm going to compare this to function of B, adding X to it, minus a function of just B. So the question is if I take A and I add X to it, and I take B and I add X to it, what happens? So adding a new element, And the answer is that adding x to a, the smaller set where a is a subset of b, is always going to give me a larger value. The increase that I get is going to always be larger or equal to than what I get if I take this larger set and I add this new item into it. And so submodularity is basically saying, is actually saying diminishing returns. And so if we wanted to plot something like this, plot both of these together, what it's saying is that I need a curve that looks something like this. So it says one, monotonicity says the curve is always going up and it's never coming back down. And submodularity says that if I compare the difference between any 2 points here, that this distance, then I compare like between points here, like this curve is, I'm not going to turn and go back up again really sharply, but the curve is sort of, it's getting, the gains are getting smaller and smaller. And so it's diminishing returns of what we're able to do as we add more heuristics to our set. Okay. And if we have these two properties together, then they give us an approximation algorithm. Now there's two versions of this approximation algorithm. One of them requires that we actually sample every possible heuristic that we could build. So we can start with that because that's sort of the easiest picture. And then I'll show what happens there. And this will give us our basic algorithm. And then we can sample from that algorithm, which will give us some additional error on top of that. But I'm going to get the our approximation algorithm. So what we really want to solve is this maximization. We can get the maximum heuristic possible. But for and this is, in machine learning and or certain fields of machine learning, this is a well-known approximation that says if I have monotonicity and submodularity, I can be greedy. And so the idea is this. So we're going to get our greedy algorithm. Okay, and this will give us greedy with respect to the entire state space, and we get this approximation that we're always going to be 1 minus e to the minus 1 is about equal to 0.63 of optimality. Okay, so that's what we're going to sit with the greedy algorithm. But what does the greedy algorithm do? So basically, we want D items, right? So remember, the problem up here is to select D heuristics. And we have this entire set C. So what we're going to do is we're going to say repeat D times to get our D heuristics. And so this is what we're going to do is basically a greedy selection here. So we're going to compute. So this is for all. And I'm just going to use H here to make things simple, but for all H, where H is going to be things that are an element of C. C is our total set of heuristics, but we don't want to include to it, so this is set subtraction of H of T minus 1. So what's going on here? H is going to be my set of heuristics at any particular time. So I'm going to say at each time step, I'm going to add a new heuristic to my set H. Initially, my set H will just include the default heuristic. So I think about all heuristics where that I haven't assigned yet is basically what this is saying. Take all heuristics that are not in my set so far. I'm going to compute. What I'm going to compute? I'm going to compute the sum over ij. And I'm just going to simply compute how much more this heuristic would add to my overall heuristic. And so it looks like this. What I'm going to say is h of ij minus h of h being my set at t minus 1 of ij. And I'm using this plus operator here. So this isn't the absolute value, but what this is, these two pieces here with a plus on them are saying take how much this heuristic gives me more information than the heuristic that I had before. So we're looking for all pairs of states in the state space. How much would this heuristic improve? Because in the end, I'm going to take the max. So I'm wanting to know essentially how much does this heuristic improve over what I have already? And I'm going to add that up. And so I'm going to choose, and what I'm going to do is add greedily. Add. So select add greedily, which is just the best H, to capital H, which would be H of T. Okay. And so this is just the greedy, it's a greedy approach for submodularity. So what I'm computing is how much does this heuristic add to my heuristic so far? Sort of if you think about here in this picture down here, I've got some heuristic value from H of T, and there's many different heuristics I can add in my next step. And the different heuristics are going to add a different amount to my overall heuristic computation. And so I'm going to choose the one that gets me to go up as much as possible. Okay. So I'm going to, so what's going to happen is I'm looking at, and of course this is all pairs shortest path. I'm going to look at which heuristic is the, or sorry, yeah, this is all pairs, not all pairs shortest path, but I'm looking at all possible pairs of states, which heuristic adds the most. But if I'm thinking here, if this set is the set of all possible heuristics, then that is sort of the set of all possible states in the state space. And so this is sort of like an n-squared process. This could still be quite expensive, but I'm going to, in the end, be left with a set of just D heuristics. So I'm going to repeat this D times. So maybe I'm willing to do that for all states in the state space to get this subset, which is going to give me a lot of information. And therefore I can compute the gain that I get by adding this next heuristic. And then I greedily choose the one that gives me the best gain. And that's how we get this approximation. But you can do further approximation, because what you can do is you can sample. So instead of doing all ij in the entire state space, is I can basically choose a set of states that I'm going to sample on. And I'm going to sample and just ask what is the heuristic that gives me the best gain over the states that I've sampled. And I might choose a subset of heuristics, not every possible heuristic, but maybe a subset of states that look like they have good heuristics overall. And so if I do that, then I'm going to get, those are going to give us some additional approximation factors that have to do with like how much error can be introduced by my sampling of the state space here and by sampling in the choice of heuristics that I have. But overall, what we see here is there's a very nice procedure, because heuristics in general are monotonic and submodular. That means that anytime I want to choose a subset of heuristics from a larger set, that I should get a set of states that I'm going to use to evaluate those heuristics. And I'm going to choose the set of states that, whenever I choose the next heuristic to go into my set, I'm going to choose the one that gives me this maximum gain as a greedy addition. And so this, as an approach overall, works very well, for instance, with differential heuristics. It gives us very actually much improved heuristic values over many other selection processes that were tested. This work was primarily done by one of my former PhD students, Chris Rayner. And so if you're interested, you can check that paper out, and you'd be able to see the full details and the rest of the math that I sort of glossed over here. But overall, this is a very important procedure and is a great way for choosing heuristics out of a set. And so we're going to continue to look at some other things going back to these differential heuristics. We'll look at some of the things we can do to compress them, which is a very interesting process where we can basically keep most of the value without losing very much information. And then the second thing we'll look at is that we can, we can compress them without losing very much, or we can increase the diversity while maintaining a similar size of heuristics and then have better heuristic values overall. And the second thing we'll be looking at in upcoming related to this is we'll look at other embedding techniques. So we can see how we could write as an overall embedding, and there's a very nice, efficient procedure called FastMap, which has been proposed for doing embeddings in, for instance, two-dimensional state spaces. And we'll get to have a look at how that works in practice. So we will see you in these upcoming lectures.